Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So for part number 2, we will discuss about steady flow process for the open system. Okay, now we will discuss about the conservation of mass principle for the steady flow process in open system. So in previous part, we already introduced the mass balance equation for the open system. Okay, in terms of mass form, the equation will be the total mass in minus total mass out, okay, equal to delta mcv in kilogram. So in terms of mass rate form, so we will have total m dot in minus total m dot out equal to dmcv over dt in kilogram per second. And here we have the what I call this schematic diagram that we have discussed before. Just want to show that we will have two different state, initial and also final state. So for this system, we have two different inlet and one outlet, and we can see the difference in terms of mass of the control volume for the initial state to the final state. Okay, so for steady flow process, the term for dmcv over dt will be 0 in the mass balance equation. Okay, so the purpose for the steady flow process, actually we want to simplify the equation. And now we will have, after we neglect or equalize the value of dmcv over dt equal to 0, so we will have the new mass balance equation for the steady flow process, where we have total m dot in equal to total m dot out, where we know that mass flow rate m dot equal to rho density multiplied by a cross section area multiplied by average velocity v bar. So substitute into the equation, so we will have what I call the equation in terms of rho a v bar. So we have here total a v bar in equal to total rho a v bar out. Special for incompressible flow, especially for the liquid, where for the liquid throughout the process the density will be constant, so we can simplify more the equation above, where now instead of we have rho a v bar, so now because the value of density is constant for the liquid, so we'll have total a v bar at the inlet, or total a v bar in equal to total a v bar out. Okay, so for a v bar formula also equal to cross section area multiplied by L divided by T. L stand for length, T stand for time. So L over T actually represent what I call the equation for V bar, average velocity. Okay, so we elaborate more. So we will have A V bar equal to AL divided by T. AL actually equal to V volume. So we have here A V bar equal to V divided by T, also equal to volume flow rate V dot. Okay, so for the liquid or incompressible flow, so the equation will be total volume flow rate in equal to total volume flow rate out. The unit will be meter cubic per second. Okay, so this is basically the mass balance equation for this steady flow that we can use. Okay, so the equation shows the general equation in terms of mass balance equation, and also the equation that involves is liquid, which is the density is constant. So we can use what I call this equation to solve the problem of the open system when involved is mass balance equation. Okay, now example 4.2. So we want to try to look at a simple example for the mass balance equation. The problem involved is application of mass balance equation. So consider an open feed water heater with a steady flow process as shown in the figure. The superheated vapor from a low pressure turbine affect the heater with a mass flow rate of 6 kg per minute and mix with the saturated liquid from a condenser with a mass flow rate of 3 kg per minute. Determine the mass flow rate of the mixture. Okay, so we have this diagram. Also for this case, we have two inlet and also one outlet. Okay, inlet represented by number 1 and also number 2. Outlet represented by number 3. So at the inlet, we have superheated vapor from a low pressure turbine. At the inlet number 2, we have saturated liquid from the condenser, and also we have what I call the outlet of the open feed water heater, OFW heater. At state number 3. So this is a simple question. So we have mass balance equation where M in dot minus M out dot equal to dmCV over dt. So because the question involves this what I call the steady flow process, so we can ignore the value of dmCV over dt, which is equal to 0. Okay, the remaining term will be M dot in, total M dot in minus total M dot out equal to 0. So substitute whatever mass flow rate that involved in the system. So now we have two what I call M dot in, which are M1 dot plus M2 dot minus M3 dot equal to 0. So substitute all the what I call value that we have for the mass flow rate. M3 dot represent the what I call mass flow rate of the mixture at the outlet. So just rearrange the equation. So we'll get the mass flow rate of the mixture M3 dot equal to 9 kg per minute. Okay. Okay, so this is just simple problem involved with mass balance equation. Okay, another example what I call that related to the mass balance equation. So we have example 4.3. The example involves reheat regenerative Rankine cycle with feed water heaters. So this is just what I call the name of the cycle. So later on in thermodynamic 2, we will learn this cycle or this system. So this example just want to I call to check your understanding about the mass balance equation for the steady flow process. Okay. Okay, now this is the complete I call the schematic diagram or flow diagram for the reheat regenerative Rankine cycle with feed water heater. So we have numbers of states involved, start from number 1 until number 16. So we know that mass balance equation for steady flow process, first we have the general equation where we have M dot in, total M dot in minus total M dot out equal to dmCV divided by dt in kilogram per second. So for flow process, for steady flow process, the term for dmc over dt will be 0. Okay, so I want to ask you about the specific mass balance equation for different what I call equipment or different system in the cycle. So we have numbers of components inside the cycle. Okay, so now this is the equation for the steady flow process that we need to implement in order to obtain the specific mass balance equation for the individual equipment or component or system. Okay, how about the boiler? So now let's say we want to determine the mass balance equation for the boiler. So we need to identify which part is referred to the boiler. So this is the boiler. So we need to identify the number involved at the inlet and also at the outlet. Okay, so for the boiler, as we look in the flow diagram, so we have 2 inlet and also 2 outlet. For the inlet, we have number 8 and also number 11. For the outlet, we have number 9 and also number 13. Okay, so by using mass balance equation for the steady flow process, we just substitute the number for the mass flow rate. Okay, so now we have for the inlet, we have M8 dot plus M11 dot minus M9 dot plus M13 dot equal to 0. So this is the specific mass balance equation for the boiler. Okay, so elaborate the equation. So we have M8 dot plus M11 dot minus M9 dot minus M13 dot equal to 0. So this is the equation. Okay, the final equation for the boiler. How about the mass balance, specific mass balance equation for pump number 1, pump number 2, and also pump number 3? So what you have to do, you need to identify where is the pump number 1, pump number 2, and also pump number 3. Then identify how many inlet and also how many outlet that involved, and also the numbering that involved for the inlet, and so numbering that involved for the outlet. Then substitute into the general mass balance equation for the steady flow process. Okay, so then try to get also the specific mass balance equation for high pressure turbine, low pressure turbine, condenser, open feed water heater, closed feed water heater, and also the mixing chamber. So if you can get the correct equation for each individual component in this cycle, so probably you already understand the basic of the mass balance equation. Okay.